Hello students, this is Professor Harosh Patil. In this particular video, we are going to deal with design of singly reinforced beams by the method of limit state design of beams. And before starting the design problems, we shall discuss the design steps involved in the design of singly reinforced beams and what will be the data given for the design of singly reinforced beam. It means what will be the known things. Here clear span of the beams will be known and live load of the beam will be known. Live load acting on the particular beam will be given, and type of support will be given, and type of concrete and steel. Type of concrete means it is characteristic strength of concrete and characteristic strength of steel. They will be mentioned over there. Now what we have to design? We have to design the depth, that is capital D, and breadth and dimensions of the beam, and the area of tension reinforcement means AST, that is area of steel. We have to find out how much amount of steel we have to insert in that particular beam. We have to find out it here. And next, shear reinforcement, that is shear reinforcement in the sense stirrups, number of stirrups we have to find out. Let us see the design steps. Okay, now first and foremost thing is we have to assume the effective depth of the beam. First we have to assume the effective depth of the beam. How we have to assume means, here effective span divided by effective depth is equals to 10 to 20. There is a criteria, L by D ratio should be 10 to 20. It differs for different spans. For a 3 to 4 meter span we have to assume it 15 to 20, and for 5 to 10 meter span we have to assume it 12 to 15. If it is span is exceeding 10 meters, we have to assume it 12. Okay, now let us see what is overall depth of the beam. How we are to overall depth of the beam, that is capital D, is equals to effective depth plus effective cover. Effective depth means it is a small d which is excluding cover, and means if you consider overall depth means it is including cover of concrete. Effective depth plus effective cover, that is d is equals to small d plus 50 mm, that is assumed cover. It is 50 mm assume, just 50 mm is almost 1 inch cover we have to assume it here. Okay, next, breadth of the beam. How we have to calculate the breadth of the beam? Breadth of the beam is equals to 1/3 of d. Whatever your d will be there, that d, it will, the breadth will be 1/3 of this particular d to 1/3 of d to 2/3 of d. In between that we have to assume it. The general width of the beam used are 150, 200, 230, 250 and 300 mm according to the sizes of beam and formworks. Usually the breadth of the beam and column sizes and beam sizes will be taken as multiples of 3 inches. Please remember, multiples of 3 inches we are going to take it, like 9 inch, 12 inch, 15 inch, 18 inch, 21 inch, 24 inches, like that. Multiples of 3 inches, the depth of the beam as well as width of the beam we are going to consider. Okay, now effective span L is equal to effective span L. Effective span L must be least of the following criteria. Which are this following criteria are? Two criteria will be there. The first one is effective span L is equals to clear span, that is capital L, plus bearing. Bearing means it is the size of supports, size of one support. Okay, effective span L is equals to clear span, that is capital L, plus effective depth, that is small d. Okay, it is the effective span can be taken as least of these two, clear span plus bearing. Bearing means the size of the support, and clear span plus effective depth, whatever the effective depth you have considered. The least of these two, whichever is this least, that value we have to take here. Next, the calculation of load. the load calculation will come. After this, the fourth step is load calculation. First step in load calculation is the calculation of a self weight of the beam. First we have to calculate self weight of the beam. How we are going to calculate it? Let us see. Now self weight of the beam is equals to B into D into density of RCC. This B is a breadth of the section and depth of the beam, and density means density of concrete we have to insert here. Then it will come in kilonewton per meter. Now next is live load. The live load will be given, just substitute, that is if it is 1.5 kilonewton per meter to 2 kilonewton per meter, the live load will be given, or that live load you need to input here. That's it. Now we have to calculate the factored load or else ultimate load, we call it as WU, factored or a ultimate load. We have discussed this in the previous classes. Okay. The WU, that is equals to 1.5U into W, that is equal to WU is 1.5U. Then we have to factor the load, this total load, that is self weight plus the live load will gives you the total load. That here WU is equal to 1.5U into W. Next, the calculation of a bending moment. Next, fifth step is calculation of a bending moment, maximum bending moment. How we are going to calculate for a simply supported beam carrying UDL. Okay, here if it is a beam, it is for a simply supported beam carrying a UDL, that is uniformly distributed load. For that you people are having a formula of WL square by 8, WL square by 8, WL square by 8 it is, but here we have to consider the ultimate load, that is factored load, WL square by 8. Maximum bending moment is equals to WL square by 8. And maximum bending moment for a cantilever beam, if this is for a simply supported beam and this is for a cantilever beam, MU is equals to WL square by 2. This is the formula. Now after this what we have to do? We have to do the check for depth, whatever the given depth is correct or no, whatever the provided depth, whatever here we have provided some depth, we have assumed the depth, and we have provided here whether it is correct or no. We have to check it, check for effective depth D. How we are going to do it? Equating factored moment is equals to limiting moment of resistance, that is factored moment is MU, whatever you got it here, that you have to take it, and limiting moment of resistance MU is equals to that is the standard formula which is there in your IS 456 2000, that is MU is equals to 0.138 FCK BD square for Fe415 steel. For Fe415 steel, MU moment, limiting moment of resistance, is equals to 0.138 FCK BD square for Fe415 steel. Now you take this D this side, that is D is equals to square root of MU divided by 0.138 FCK B. D is equals to this 0.138 FCKB goes this side, and this D square, it becomes a square root here, that is square root of MU by 0.138 FCKB. This is D required depth. Okay, this D, if it is less than required depth D, assume if it is less than the assumed depth, hence the design is safe. If it is more than the assumed depth, the design is not safe, hence revise the depth of the beam, means we have to increase the depth of the beam. If this value is more than the D provided, we have to increase the depth of the beam. It means it is going to fail, the design is not safe. Okay. Now the next step is the seventh step, calculation of area of main reinforcement. Main reinforcement in the sense we have to calculate the area of steel, whatever we have to provide at the bottom of the beam. You already know main reinforcement in a simply supported beam, it will be there at the bottom. So AST is calculated as follows: mu is equals to 0.87 Fy AST into D into bracket 1 minus square root of AST by BD into Fy by FCK. This is the formula for calculating mu. Okay, mu, and solve for AST. Now we have to solve it for AST. Okay, the next after this this is one type of formula, or else you are having one more formula to calculate the AST. First you have to find out percentage of steel PT, that is 50 into 1 minus square root of 1 minus 4.6 mu by FCK BD square divided by Fy into Fy by FCK, sorry. Okay, percentage of steel, that is PT, you will get it here. Therefore area of steel AST is equal to PT by 100 into B into D. The PT is a percentage of steel it here. Now assuming suitable dia of bars 8 mm, 10 mm, 12, 16, 20 mm dia, 20 or 25 mm dia bars, we have to assume it. We have to assume the suitable dia bars. Now therefore number of bars is equals to total AST divided by area of one bar. Therefore number of bars is equals to total AST divided by area of one bar. That is in simple words we'll call it as capital AST divided by small AST. Capital AST divided by small AST, we can call that. Capital AST in the sense total AST required for the here whatever you people have got, that is, and area of one bar. Area of one bar, pi by 4 into d square, we have to do it, and we have to find out the area of one bar, and we have to input the value here. Next, first note, minimum number of bars should be 2. At the bottom, minimum number of bars should be 2. You should not provide only even only a single bar. Okay, minimum number of bars should be 2. Okay, next is a design of shear reinforcement, that is stirrups. We have to vertical stirrups, we have to design the vertical stirrups. That is calculate shear force. Vu is equals to WL by 2. You already know the formula for shear force for a simply supported beam carrying UDL, that is V is equals to WL by 2, and Vu for cantilever beam W into L, that is the Vu is equals to WU into L. For we are doing it calculation for ultimate load. For that reason we have written it is here Vu and WU. Okay, the next is nominal shear stress. We have to find out the nominal shear stress for in the design of shear reinforcement of stirrups. Shear stress is tau V. Nominal shear stress, we'll call it tau V. That is tau V is equals to Vu by BD. Vu divided by BD. The percentage of steel, how we are going to calculate the PT is equals to percentage of steel, and PT is equals to AST by BD into 100. Here for this particular value of tau V and tau V you will be calculated here, and for the tau C refer the table number 19 IS 456 2000. Here for tau C value we have to refer IS 456 2000, the table number 19 for tau C value. Okay, if tau V is greater than tau C, if tau V is greater than tau C, here tau C in the sense it is permissible shear stress, tau V is nominal shear stress. If tau V is greater than tau C, then shear reinforcement is to be designed. Then shear reinforcement is to be designed. Then shear taken by concrete is equals to tau C into BD. The next step is shear taken by concrete is equals to tau C into BD. Then shear to be taken by stirrups, VUS. This is the one more formula here. Shear to be taken by stirrups, VUS, that is equals to VU minus tau c into BD, VU minus tau c into BD, assuming 6 mm or 8 mm dia bars for a stirrups that is two-legged. Two-legged means it is it's a two-legged stirrups. I'll show it in the figures, the design problems. Okay, two-legged means one leg and two leg like this. Just I'll show it here. Okay, this is one leg and this is another leg, that we'll call it as two-legged stirrup. This is one leg and this is the second leg, one and two. For that we'll call it as two-legged stirrups. Here we'll provide the bars. These are the main reinforcement and these are the anchor bars. Here to hold the stirrups we'll provide the anchor bars, that is at the top. Okay, that is area of stirrups. How we are going to calculate, that is ASB is equals to 2 into pi by 4 t square. Now spacing of the stirrup should be least of the following three criteria. The first criteria is spacing criteria is SB is equals to 0.87 FY by ASBD divided by VUS. This is the first criteria. We have to find out this 0.87 FY ASBD. ASB we will be calculated here and D will be known, and this VUS will be known from this particular formula, and just we have to substitute all the values here and we have to get the value, and that will be our spacing. And the second criteria is spacing should not be greater than 0.75 D, and the spacing, whatever the spacing of the stirrups you are going to provide, that should not be greater than 0.75 D, and spacing should not be greater than 300 mm also. If it is exceeding 300 mm, again whichever is least we have to provide it. That is the spacing for stirrups. Next, if tau v is less than tau c, if tau v is less than tau c, then minimum reinforcement is to be provided. Assume 6 mm or 8 mm dia bars. If tau v is less than tau c, then minimum reinforcement is to be provided. Assume 6 mm or 8 mm dia bars. Okay, next we have to do the check for deflection, whether how much deflection of the beam will occur. That we have to do check for deflection, that is note down percentage of steel provided, that is PT value. The stress in steel and service loads, Fs is equals to 0.58 into Fy divided by AST required divided by AST provided. This is the formula. The calculate modification KT from curve, refer clause number 23.2 IS 456 2000 for Fs and PT values. These values will be there in clause number 23.2 IS 456 2000 for the Fs and PT values. L by D maximum is equals to 20 into KT, that is for a simply supported beam. Similarly, L by D maximum 7 into KT, that is for cantilever beam. And if L by D max is greater than L by D provided, what we have to do is then deflection is within the limit and safe. If L by D maximum provided is if L by D maximum is greater than the provided L by D, then the deflection is within the limit and hence the design is safe here. Now if L by D is less than L by D provided, then the design the redesign the section. Hence we have to redesign the section. Okay, and after this we have to sketch the longitudinal section and cross section of the reinforcement of the details. Means how much whatever we have got cross section means whatever I have drawn earlier, like that we have to draw the cross section of the beam. What is the diameter of the bars, whatever we have got by calculating the AST and number of bars, we have to show it there like this. Just I'll one more time I'll show it the cross section. If this is a cross section of the beam, just I am roughly I am drawing here. As this is the cross section of the beam, and this is the stirrups, and these are the anchor bars, and these are the main bars here. Whatever we are going to see here, these are the main bars. Just like this you have to show it. It is a cross section, and a longitudinal section you have to show it like this. This is a longitudinal section. You have to show the supports here. Just a rough diagram I am drawing here. I'll show it in coming classes. Clear diagram will draw it. This is a longitudinal. These are the this is anchor bars, and this is main bars. Like that you have to. These are the stirrups we have to provide. Like this. Okay. Here in this particular class I am going to I am discussing only regarding the steps involved in the design of singly reinforced beam, like that. So I have designed very I have given very simple steps here for the design of singly reinforced beam. Please go through this. This is regarding the design steps involved in the singly reinforced beam. Okay, by using a limit state method of design. Okay, this is regarding your today's class. We'll solve the numerical problem on the same design in the coming class. Okay, thank you.